Yesterday, just as another reminder, yesterday we did that activity about the green car and the orange car, and I don't know if you've spent any time sort of overnight or in the afternoon or whatever thinking about it. But we'll talk about it again a little bit. The problem was, to remind you, that everything we had done in this course so far was you were finding rates of change between 2 points. And that, we only did that for a day, but that's what we had done. And then that question said, what was the speed of the car at that instant? And a lot of you have seen that before in physics. You draw a tangent line and you can do that. But the tangent line that you draw, like in a physics class that you've done that way, is an estimation, because it's quite frankly really hard. Like I saw some of the groups, actually some of them are still up. There's a estimation of 22, I think you got, or 20 meters per second over there. Somebody else got 22 maybe. And those are good estimations because, like, graphically, it's hard to do this stuff. This group actually got the closest answer. If you notice, these are actually right because they rounded, but they're actually, both members aren't here, it was Claire and John, and they rounded a little bit, but they kind of used the estimation technique we used yesterday in class. They actually got the exact right answer. So those are the right answers for that problem that we were doing yesterday. But it wasn't, the right answer wasn't the point. The process was the point. And so when you're drawing in your own tangent line, okay, you are estimating, and it's hard. If you're on a turning point, it's easier. You probably found the, which car was it? The, oh, there it is. The green car, which was like the exponential graph. That's really hard to draw an accurate tangent on that and pick 2 points. Like that would be really, really tricky. And so you'd expect that one to not be as accurate. And actually, this group over here who did it, 1.77, that's a pretty close estimation to 2, right? These are both estimations. They just happen to round and get it right. But in physics class, when you're drawing in a tangent, it's an estimation. So in math, obviously, we want to know, is there a way to calculate it, not estimate it? Estimating's fine in some circumstances. Is there a way to calculate it? But our formula only works when we're given 2 points. Okay? If I try to use 1 point and itself, I get 0 over 0, and that won't work. We remember our example from yesterday, one of our examples, right? If I'm using 2 different points, I get 2 y values, that will work. If I'm using 1 point, I get 1 y value, and subtracting itself 0 over 0, that's not going to work. So what can we do? So one thing we noticed yesterday, and a couple of groups were getting close to, was, well, if I pick points that are really close together, I get a closer estimation, and this is kind of what the process we did together. I get a closer estimation of the exact answer. And you can see that the closer I pick my 2 points, so 1 is where I'm trying to find the actual slope of the tangent. So 0.5 and 1, 0.9 and 1, 0.99 and 1. I'm getting closer and closer and closer and closer to like 2 points that are really close. These 2 points here, you almost couldn't tell the difference unless you zoomed way in if you were using a computer, right? And I get really close to my answer. And you can see that the slopes are approaching something. And you can see here that the slopes are approaching something. And from the left and from the right, they're approaching 2, both of them, right? From above and from below. We've talked about that kind of process before a little bit when we've talked about asymptotes. So you can kind of see that estimation technique works. But what if we don't even want to estimate this way? This is still an estimation. What if we want to actually calculate it? That's our ultimate goal, and that's what we're working on. And so that's when we need to bring in this concept of limits. Okay? So let's scribble a couple of things here. Remember when we talked about functions with holes a couple of units ago? Do you remember doing that? So imagine I have a function and it's got a hole in it. Now, why do we want to talk about a function with a hole? If I think about one of the examples that we did yesterday, it looked like this. X cubed. I don't know that you have to write this down. You can just watch if you want. When we use the difference quotient formula, this is what we ended up with. We did f at x minus f at a, right? We did that process. Here it is. It was this question. And we did all this trickery with limits, which people didn't really understand. Why are we doing this weird notation? What's going on here, right? But we did this process, and partway down, there it is, we ended up with that line, x cubed minus 1 over x minus 1. So we ended up with this expression, which in and of itself is like a function. Isn't that right? That, like if I cover everything else up, that's a function. In fact, that's one that we may have graphed in Unit 5. Okay, so after we had done all the subbing in, we ended up with this expression or this function. And then we did this. We had the limit notation, but we did this. This is x minus 1 times x squared plus x plus 1 over x minus 1. Well, what is this? This is a function with a hole in it. Isn't that right? Now, this is not the function that you were given in the question, so be careful. Don't get confused. This is the function that arose from the difference quotient when we subbed in and did a little bit of work in solving. So, but this function, if you think of it as a function in and of itself, has a hole, x minus 1 over x minus 1. And what is a function with a hole? Well, a function with a hole is a function that basically is this function, the red function. It behaves exactly the same as the blue function everywhere except for that one little point, except for where that hole exists. But everywhere else, though the blue function and the red function are exactly the same, right? That's what we mean by a hole, okay? So if this function, if the red one was like x minus 3 all squared minus 2, so it's just a parabola that's been shifted over and down, the blue function with the hole would have a slightly different equation, but otherwise they would both behave exactly like that parabola. They would behave exactly the same everywhere except for that hole. And when I say everywhere, I mean everywhere. Like you could get really close to that point, really close to that hole, and they're both still going to exist. And then you can get even closer. We can always make numbers smaller. If that hole occurs at x equals 5, I could get up to 4.9, 4.99, 4.99999, 4.9999999. Like I could get as close to 5 as I want. And both those functions will be exactly the same until I actually end up 5. Do you agree with that? Do you understand? Like that's what a hole means? So folks, that's what the limit notation from yesterday also means. It means x is approaching 1, but it's not equaling 1, but it's approaching it as close as possible, and we're considering the behavior as x approaches 1. Does that make sense? That's about what we need to know about limits, I think, for this course. I said this yesterday. If you take calculus, calculus is all about limits, so we explore that a little bit more, but that's the idea. And so then, what this algebraic process does, when we take that hole and we actually eliminate it, is because we don't really care about this function. We care about the function where that hole is. But we can use the red one, okay, to look at what's happening where the hole is. It doesn't matter that there's a hole there. We want to know what's happening there anyway. So we can use the red function to peek at what's happening there. The red function is the one that doesn't have a hole, behaves like the blue one everywhere, and will behave like the blue one would at that location if it didn't have the hole, right? So we can remove the hole, use the remaining function to peek at what's happening, and use that to answer our original question. Our original question was, I can't divide by 0. But can I do some trickery to remove those zeros, peek at what's happening, and then I don't have to worry about it anymore? Does that make sense? So that's the general idea algebraically of like how that algebraic process works. Is we're generating this function. Yes, it has a hole, but we're doing some sort of algebra trickery to get it out of the way, look at what's happening, and so when this goes away, look at what I'm left with. I'm left with this quadratic that exists everywhere. It doesn't have the hole. So I can check what would have happened. Now I can check where the hole was, what would have happened. Because this function and this function are the same general behavior everywhere. Does that make sense? So that's the idea of why. So it's important to write the notation correctly because, as you know, communication is important, and that's how it's written. But that's the why. Okay? And again, it all stems from that idea that I can get 2 points that are really close and estimate, but I can't have 2 points on top of each other. That just won't work because it's 0 over 0. Okay, let's take a look at another polynomial example of this process. So this is the polynomial type. I said there were 3 types. One of them is polynomial. This is the polynomial type, one of the 3 types algebraically that you kind of need to have to solve. So one of the first steps, I would say maybe the best first step is if it gives you, sometimes it gives you the point. If you looked carefully at the homework, some of the questions give you the whole point, the x and the y. But if it only gives you the x, then the first thing we're going to do is find the y. So go ahead and figure that out. Sub 3 in. What'd you get? 0? This is kind of nice when it works out to 0. It makes some of the math a little bit easier, but hopefully you got 0. Don't go any further. If you didn't get 0, be careful. And it's an indication that certainly can happen. You could get any value. You could get a fraction here. I mean, I don't think we see that too often. It makes the math quite a bit harder, but anything can certainly happen there. Okay. So now we do our slope of the tangent. So our first statement, you saw we did this in both examples yesterday, is we're basically just writing the formula. This is our formula. The limit as x approaches a, and eventually x and a are going to be the same. This was the question that Emma was kind of asking, like, which one's x, which one's a? Eventually they're both going to be the same. They're both going to be 3, but I can't do that yet. And again, it's funny how this feels like a complex process. And it is. I mean, I said this before. This took hundreds of years to develop. And then all of a sudden it was developed and it became calculus. And I can't tell you how many big questions in mathematics were solved at the time when this was invented. And like the impact of this lasted and still lasts to this day. Obviously, it's one of the biggest branches of mathematics is calculus. It's such a big idea, but I mean, that formula is from grade 9. It's just slope. That's all it comes from, is this simple, it's just the slope formula, right? So tie that to your previous knowledge. Don't overthink it too much. That's just the slope formula, okay? So f at a and a are going to be, and I wouldn't always write this out, but just for our note, you might want to. So a will equal 3, and then f at a will equal 0. These are the values that we're given and that we calculated, and that's what I'm going to do in my next step. So now this equals the limit as x approaches 3, and see how I sub 3 in for a there too, of f at x, which is our function, so negative x squared plus 2x plus 3 minus f at a, which is 0, over x minus a, which is 3. So those are the values that I subbed in there, right? So we're subbing in a at that point because now we want x to approach 3, not for x to continue to approach a. Sometimes, we saw this yesterday in one example, we do leave it as the a and we just do it algebraically. And we'll see an example of that tomorrow actually, where there's a type of question where we want to solve and we have to do it that way. Everybody okay? Now we do just some sort of expanding and simplifying. Although in this, actually I'm going to rewrite it, although probably normally you wouldn't. Because it's minus 0, there's not much to do. But so this is negative x squared plus 2x plus 3. This is where, this is where the other two types of questions are different. The algebra is going to look different, but ultimately we're working towards something that's similar. But the algebra here, to get it into a particular form, will depend on which of the three types of questions you're kind of looking at. Does anybody, what do you think we should do this time? Yeah, very nice. So negative x squared minus 2x minus 3. Why are we going to do that? Because we're just going to factor it. With these polynomials, we're always working towards factoring. So go ahead and factor that. Pretty easy factoring by our standards at this point, I think. And what happens here? We get x minus 3. Remember from yesterday, that has to happen. But every year there's like somebody who's like, oh, you know, I did all the math and I think I did it all right and it didn't work out. Whoa, no. It is going to work out. It has to. This process will not fail. So if for some reason it hasn't worked out, maybe you're working for whatever reason, I don't know why you'd be doing this, but with a function and you're not like a different kind of function than what we've looked at, and there's a reason why, or you've made a mistake in the algebra, or just in your computations, like a negative or something probably dropped, right? Or even sometimes, honestly, it's that step right there that's the problem, is people make a mistake calculating this. Or they forget to calculate it, and they just put 3 in for both, or something silly like that. That's often the mistake, okay? So be careful. This process will always work. But that's a good like place to have in your mind where you're working towards to see that it works out. Go, okay, I'm on the right track. Okay, and then what do I get? I get equals negative x plus 1. This is going to be negative x minus 1. And what have we done here? We've removed that hole in the function. And now in this function behaves exactly like the other ones above it, everywhere except for in that hole. And I can use it to check what's going on with that hole. It's this funny little process where it's almost like, remember from that activity we did yesterday, you can't find the instantaneous rate of change at a single point with that slope formula. It's not going to work. So it's like we're tricking the math. It's kind of like, hey, look over there. And then you do all this math and you go, oh, okay, yeah, you can look again and now we're fine, because we've changed the function. We can't do it up here. I think people ask this question, why can't we do it up here and we can do it down there? Like, how is that okay? What about all those restriction stuff that we talked about? But in this case, because of what we're doing, it works. Okay. All right, so now what do we do? Now, once we've got our simplified function, we can actually sub x in, and that's when we no longer need the limit statement. So it equals -4. Any questions about any of that? I'm just going to show you one little thing about this. So the original function was -x squared plus 2x plus 3. Is that right? There's what that graph looks like. And it wanted to find it at 3. So f at 3, right? When x equals 3. Oh, whoops. I need an actual point. 3 and f at 3. So there's my point, 3, 0. What is the slope of the tangent going to look like at that point? This is what we're finding. I mean, all this talk about instantaneous rates of change, we're also just calculating slopes of tangents. That's why I call it m tan, right? The slope of the tangent. So if you're just asked to find the slope of a tangent, this is how you do it. If you're talking about cars moving and you've got distance, you're looking at like acceleration or speed or something like that, or rates of change in a word problem, an application, then you're finding the instantaneous rate of change, which is the slope of the tangent at that point. But what would the slope of the tangent look like? Well, it would be negative, wouldn't it? And it'd be relatively steep. So our answer fits. -4 fits. Any questions about that? All right. Let's try the next. I think this next one's going to be the next type. There we go. Type number 2 is a rational expression. What's our first step? Very nice. So -7 minus 1 over -7 plus 3. You do not have to show this work. I'm just showing it for the lesson's sake, which is -8 over -4, which is 2. See what I mean? Imagine if you just made a careless mistake there. And this is what happens when we're doing more complex processes. Our brain is working really hard to think about that, and we end up dropping a negative somewhere. Okay? And if you start with the wrong thing there, it is not going to work. So you really want to make sure that you get that part correct. Okay, here's a formula. So the limit as x approaches a So f at x is the function x minus 1 over x plus 3 minus f at a, which is the 2 over there, all over x minus a, which is negative 7. So it's going to be x plus 7. Put your pencil down and watch. This is the important step of how you solve this type. There's two sort of denominators that you could think of in this question. And we're going to use one of them. And if you use the wrong one, what you're doing will quickly not work. And hopefully that will remind you that, oops, I used the wrong one, because I definitely see people doing that. We're going to use the denominator of this guy. Okay? And what we're going to do with it is multiply it on top and on bottom of the entire thing. So we use the denominator of the original function, but multiply it on the top and the bottom of the whole difference quotient function. And because I'm multiplying by 1, that's okay. That's something we're allowed to do. And so this ends up being sort of distributed into the top. So normally I would skip this step, but I'm going to write it out this time. So it's x minus 1 over x plus 3 times x plus 3 minus 2 times x plus 3, right? So it gets multiplied by both things on top. And then I've got my x plus 7 on the bottom, and my x plus 3 as well on the bottom. And once you've got this part set up, if you've done this correctly, the rest works out fairly simply. The rest of the algebra for this one typically is pretty easy. Of course, it could get harder if we give a slightly harder question or different numbers, but I notice that this and this are gone. That was the point of that. That was the whole reason why we did it, so that we don't have a rational in a rational, right? We don't have a fraction in a fraction. Now we just have one whole big polynomial, or sort of rational expression. Limit as x approaches negative 7 of x minus 1. And I can expand this, minus 2x minus 6. And I certainly don't want to expand the bottom. Look carefully at this step. I still can't sub in negative 7. Because when I put it in here, I'll get 0. The whole bottom will be 0. Regardless of what I get on top. Maybe I get negative 7 on top 2, or 0 on top 2, maybe I don't. But I can't divide by 0. So I know just looking at this step, if I put negative 7 in, it's not going to work out. Okay? So we have to keep going. X minus 2x is negative x. And negative 1 minus 6 is negative 7. See, that was pretty easy. And what am I going to do? I'm going to factor the top, just a common factor. And there we have it. It worked. See how it worked out again. And it has to, every time, all the time. So this is a negative 1 on top now over x plus 3. I've removed the whole. And now I can actually sub it and solve. So the slope of the tangent is 1 over 4. Any questions about that one? Mm-hmm. Like one of these.
Yeah, and it seems like sometimes the denominators of the f of x function would be remain the same like at the end before we settle over x. Because it would always like it would be the same function that was in the denominator. Like once you divide by
Yeah, then it's not working?
it would work.
It would work.
Yeah, because like would have
Oh, that's fine.
yeah.
That's a coincidence kind of though.
But then like you have to
I don't know, that must be just the way that they're set up. Sorry. It's not that big of a coincidence. It's because when we multiply by x plus 3 over x plus 3, so that like we multiply by the denominator of that function. Actually, sorry, that's likely to happen, but it's irrelevant whether it happens or not. That doesn't matter. It's not that we can't divide by this, the x plus 3. So what Asya is talking about is this up here. Like, see how it worked out to x plus 3 here? And then the next one was x plus 3 at the end? That's fine. The fact that this was x plus 3 wasn't the reason why we couldn't do it. Right? The fact that it was x minus a, and then a is negative 7 and x is negative 7, that's why we can't do it. It's got nothing to do with this. It has to do with this. It has to do with this denominator, why we can't in the formula. Does that make sense? Does that kind of answer your question? Okay. All right, here's the last kind. So the first part of it is all the same. You can go ahead and get that part started after you've written the question down. It looks like most people, or at least most people on that side of the room, got this far, which is, I would say, about as far as you could probably get without knowing the sort of steps that you could try. I don't know what you might try. You may have seen something like this before. But you should at least be able to get to this step because it's the same. So I just found the y value, f at 8, and found it was 2. And make sure you get the 2 and the 8 in the right place. Don't get them in the wrong place because this is f at a, which is 2. It's the function that's been evaluated. And this is just a on the bottom, right? It even says in the formula a, which the confusing part is that it actually says x up here and we're subbing in for a, but hopefully you kind of are picking up on why that is. Anybody have an idea? Yeah, go ahead.
Sorry, why do we only take the positive 2? Does the negative 2 not matter?
Does the negative 2 not matter?
It's usually like if we're taking like just a square root and
That is a good question. So the square root function doesn't have the other part.
Okay.
So if we're thinking of it as a function, then we only need to think about that. Otherwise, if you picture the function, the slopes, like I'm picturing the function, I go over 8 and I go up 2 or I go down 2. The slope's not going to be the same. Like it's going to be the same value, but it's going to be positive in one case and negative in the other, right?
Yeah.
So that comes from the fact that the function, if there was a negative out front, then you would. That's how you would think through that one. Okay, does anybody have an idea what you might do here? Any clue? You have seen sort of stuff like this, maybe more in grade 11 than anything, but. Do you remember the radical conjugate? Vaguely? No. Sort of. Yes, actually, the result of what we do will do that. But how do we do it is the question. What's a conjugate? So I'm going to multiply the top and bottom by the square root of x minus 4 plus 2. And once you know what this process does, you can skip this step, but I am going to write it out once just to make sure people can follow why it's doing that. But it's long and it's the same thing every time. This is kind of like a difference of squares idea, right? So we know that the middle term is going to add to 0. But this is going to be so if you want to just watch, it's going to be square root of x minus 4 times the square root of x minus 4, and then the square root of x minus 4 times 2, and then negative 2 times the square root of x minus 4, and then negative 2 times 2. Right? That's how it's going to work. We're actually doing the full distributive property on top here. So this is going to be the square root of x minus 4 all squared plus 2 times the square root of x minus 4 minus 2 times the square root of x minus 4 minus 2 times 2, which is minus 4. And then on the bottom, I'm not going to expand anything. I'm going to leave it as x minus 8. Don't forget about the bottom. And I need a bracket here. Take a look, put your pencil down and look. I've got bracket here and here around this whole bottom. You need that. A lot of people would drop that and then you're going to do all the math and it's going to work out anyway, but that's still like a communication error if you drop those brackets. So these big brackets around this whole thing, it's this times all of that. So you need those brackets in there to be consistent. What is x minus the square root of x minus 4 all squared? It's x minus 4, good. Those are opposites. And then I look and I see I have 2 times root x minus 4 minus 2 times root x minus 4. So they're gone. And I'm left with minus 4. And you can see right away how that worked out so nicely for us. Because I'm trying to get rid of that x minus 8. Don't forget your bracket. And all of this is because we can't divide by 0. We can't do 0 over 0. So here's where we're like tricking math, like, look over there. No, I didn't do anything. And now we can. 1 over square root of x minus 4 plus 2. I'm innocent. I didn't do anything. And then we can sub in. So this equals 1 over, and remember what I said at the beginning, so this is 8 minus 4 plus 2. Let me just finish this. 8 minus 4 is 4, square root of 4 is 2, so this is 1 over 2 plus 2, which is 1 over 4. And remember, I said this at the beginning of the class, when do I get to drop the limit statement? That's something that people have a hard time with too, I think. You practice it enough, it's not that complex, and so just for form, what I would like to see is that you do this step where these divide to 1, you rewrite the final one, and then you can drop the limit statement and sub in, okay? So you do need this final step just for communication. There's a lot of other steps that I sort of mentioned that you could skip. So these are long questions, but they just are. That's the nature of this process. That's what we want to see. Any questions? Those are the 3 types: polynomial, rational, and square root. Polynomial kind of you factor, but it kind of just works out. And those polynomials could be, we've seen a couple of degree 2s, but it could be degree 3 or possibly even higher, but not likely. See too many like that. And then the rationals, we sort of saw the method for that, and the square roots, now we've seen the method.